Hello, everyone. Welcome to our session. My name is Venita Narajala. I'm a security researcher contributing to OWASP. We have many projects like the AI VSS, the Agentic Security Initiative, and a few other open source projects within OWASP as well.
Hey everyone, my name is Idan Abler. I'm an AI security researcher, a core contributor of the Threat and Mitigation Guide, and one of the co-leads of Securing Agentic Application workstream with Venita and Rob. And this is basically the guide that we are going to walk through today. So let's start. First of all, let's start with some context and the history about the workstream itself. A few months ago, OWASP released the Threat and Mitigation Guide for Agentic AI, and it truly is a great resource, an amazing and foundational resource. But we started quickly to hear from the community that they want something more. They want something which is more practical, with actionable guidance that they can follow right away and apply countermeasures and mitigations in their own application. So our mission became clear. We need to provide a community with practical guidance, hands-on guidance they can follow and apply various types of mitigations and technique in their own application to enhance the security robustness. And this is basically how the Securing Agentic Application workstream started. It's a complementary resource to the Threat and Mitigation Guide. That means that it uses the same threat landscape, the same risk, and the same mitigations technique, but it follows by real tools and practical measures that everyone can use. So in the following session, Vinith and I are going to walk you through the guide so you'll be able to consume it, fully understand it, and use it wisely. And we also have a small surprise. We are launching a new website that will help you consume the guide in a more interactive way. So let's dig in. The guide uses a methodology that consists of four main properties. The four main properties allows us the flexibility to cover a lot of agentic applications, many types of agentic applications. And we started with the development lifecycle. The development lifecycle, as you can assume, we couldn't identify single silver bullet to mitigate the entire threat landscape. So we had to think holistically and provide mitigations that can be applied across the entire development lifecycle, starting from the design phase, moving to the runtime phase. So the guide is focused on solutions. For example, let's say on the design phase, how can you build secured prompt, dividing your user prompt from the system prompt, separating between trusted and untrusted data. And when speaking about runtime phase, we are speaking about how to detect prompt injection attempts, how to detect content moderation violations. So the guide is full of practical tools and open source and commercial tools that can be used to mitigate these threats. And when speaking about the next property, which are the key components, you need to picture a simple agent. Let's say, as you can see over here, an agent is composed of an LLM, a memory module, planning module, and the tools that the agent uses. So it is very important to understand how each of these components were implemented and deployed, as it has the direct effect and the different effects and risks that inherent in your application. For example, let's take a look on the memory module. A memory module can be implemented as an isolated object or a shared object. And if the developer opt to implement a shared object, let's say share among sessions or memory that's shared among users or among agents, it comes with different types of threats and risk into your application. So the guide provides tailored solutions and tailored mitigations for each of these choices. And when speaking about tools, it's just the same. The developers could implement his own tools or import tools from third parties, let's say an MCP server, which is rogue, which is malicious. So also over here, we are speaking about tailored solutions and tailored mitigations techniques, such as the use of MCP catalog. The next property to provide a truly holistic solution are the architectures. The guide focuses on different types of architecture, starting from single agent architecture, multi-agent architecture, which is the most common with and without an orchestrator, and the state-of-art architectures, which are peer-to-peer communication. It started to rise with the pop of A2A and ACP protocols, which allows us to communicate between agents without any intermediate. So each architecture requires different type of mitigations and different layers of mitigations. When we're speaking about multi-agent system, for example, you can think about ways to harden your orchestrator or secure the communication between the sub-agents. Or when you're speaking about peer-to-peer communication, there's different types of threats that are all related to trust. How can we assure that the agent, let's say agent A, is actually who he claims he is? How can we create decentralized trust among the agents? And finally, we have the skills, the operational environment. Skills are basically the functionality of your agent with external environment. It's anything between the use of the agent let's say, web use agents or PC usage, or skills like your agent uses a RAG or connected to sensors or IoT devices. Each skills comes with inherently different types of threats and therefore require different and tailored solutions that you might require and need to implement in your application. So let me sum it up for a second. If we want to apply the methodology when analyzing a new agentic application, we need to take in mind the architecture of the application, which type of architecture we chose, what are the skills of our agent, and how we chose to implement each key component. And to provide a truly effective and holistic solution, we have to make sure that we add the mitigations and countermeasures at each stage of the development lifecycle. So to show you how to apply this methodology on real use cases, Vinith will now take control and demonstrate.
Perfect. Thank you, Dan. So, in our first example, our first use case is a really simple single agent architecture. So, if any of you are building out an agentic system, it's always advisable to start off with your most simple single agent architecture. So, as you can see in this image here, we have a single Slack agent. It has your core LLM. It has the Slack API integration, which is your tool access. It's able to it has a message processing area. It has a memory management to keep track of older messages, and you can see it has a local session, and also is able to talk to channel management tools or message automation tools and so on, right? So if you can think about some threats here that like Idan spoke about, right? It's possible like we can have issues. We can see threats in the memory, the session memory, or you can see tool misuse or prompt injection that causes Slack to delete a ton of messages. Next slide, please. So here's a really simple agent, and now let's take that single agent system, and now let's look into each individual part, like I was just talking about, right? So in the first one, in the architecture part of our SDLC, you can see that the vulnerable shared memory session is a major threat, right? What happens if you're able to poison the memory, and over time the LLM reinforces that poison memory and then acts erratically because LLMs are inherently non-deterministic and it's really hard to control, and also detect if something was poisoned really way back, right? And so you have memory management issues here. And in the next phase, the operational environment phase, you can see like what happens if your LLM via tool access has access to a code interpreter like Python, or it's possible you might have some scripts that are triggered by a Slack workflow. What happens if you trigger the wrong script and so on, right? So that's the an operational environmental threat. And then finally, if you look at the entire dev life cycle, you have other things to think about, right? You have build time controls. How are you going to enforce schema? How are you going to prevent prompt injection? How are you going to like build authentication, authorization, and trust between your tools and your LLM and your agent, right? As well as other runtime controls like content moderation. What happens if someone says sends messages that are against company policy, or um, uh, or if you start seeing like thousands of messages being deleted in the middle of the night when all your developers are supposed to be asleep, right? So anomaly based detection as well as memory screening. So in this really simple single agent system, you could see how many different paths we could have taken with so many different threats and then mitigations, as well as how they all impact various key components that Idan brought up, like the LLM, the memory, you have tools, and so on. Next slide, please. And now let's complicate this a little further, right? So we spoke about a single agent system. Now, uh, we are all moving towards a multi-agent agentic world, I would say. So you have more than one agents, especially you have very specialized agents doing a single task, because it's much easier to control for quality and accuracy when you have really purpose-built agents, right? So let's imagine you have a work colleague, also called Microsoft Copilot, one of the 70 Copilot applications Microsoft has released. They have access to this agent has access to your Slack. It has access to your calendar, your drive. So it can act like your personal assistant at work. So one architecture you could possibly deploy here is you have an orchestrator agent, and then you have various sub agents that the orchestrator controls based upon the query or the intent of the user, right? So each sub agent has access to its own tool. So you have calendar agent, a Slack agent, a drive agent, and similar. Each agent has access to tools, and then because the same is just one user's calling this one orchestrate agent, it's good to have cross agent memory, right? What if the user says, hey, can you uh, create a calendar invite with this person and then send them a Slack message with this drive link? So here you see this simple prompt requires access to calendar, creating an event, looking up the Slack username, sending them a message, as well as searching through drive, finding, creating a drive shareable link and sending that as well. So yeah, here you can now, let's break this down similar to our single agent architecture, into our various subcomponents, right? So in the architecture section, you have again shared memory issues. It's possible like your calendar agent. Let's say if one of your agent is compromised, how it impacts or cascades the issues across other agents. It's also possible that one of your agent can poison the memory, saying, hey, yes, I've completed a task, but it actually didn't and can cause failures down the line and so on, right? In the operational environment, like we said, we have API access via MCP, or maybe other protocols in the future. Your agent having access to calendar. What happens if via prompt injection, instead of creating events, it starts deleting events, right? Johann Rebecker, one of the researchers from Germany, was able to show that the initial Microsoft Copilot, the email bot, was able, when asked to summarize an email with hidden text, would actually exfiltrate Slack tokens or like delete emails and so on, right? So because your agent has complete access with your credentials, it can act on your behalf and can cause a lot of issues. And then finally, in the dev lifecycle, let's talk about build time and runtime again. So in the build time, you have similar things to think about, right? How do you enforce that the return from the calendar agent has strong schema? You're enforcing it. You're patching your prompts. It's also possible you might create a prompt database, right? So like for a calendar agent, you only have a few prompts that can be possible, like create event, delete event, modify event, and so on. And then it's really easy to ensure that it's harder to like prompt injects things like, oh, like imagine your X, or disregard all previous instructions. So if you create a trustworthy system prompt, or a really scoped down prompt, it's really easy to prevent some of these prompt injection issues. And then finally, in the runtime, again, content moderation guardrails, especially when it comes to multi-agent, the guardrails can get a little difficult. So scoping them down per agent, and then tracking them in a version control system across your entire enterprise, and also having strong anomaly based detection using trace routes, logging as much as possible, and then integrating all of these into your existing SIEM or source systems. Next slide, please. Cool. So now let's look at a case study on a peer-to-peer collaboration. So let's say you have an agent A that has a specific skill, and then agent B, which has a specific skill. They're completely independent of each other. And with the advent of agent-to-agent communication protocols that have, since the last 6 months or so, we've had A2A come out. We have ACP. We have Cisco's agentic framework, and I'm sure in the future there might be more that come out. So it's possible that you have agents talking within the same ecosystem using the same protocol. It's also possible we might have connectors and agents talking from various different protocols. So discovery of agents might becomes an issue. You also have an issue of trust and governance. Let's say you have multiple hops, right? Agent A to B and B to C. What identity should agent C get? How does agent C know who the true caller is? So you have a lot of threats uh, and like edge cases to think about, especially in a much more interconnected agentic network. Next slide. Yeah, let's take the same peer-to-peer collaboration case study and let's break it down similarly. Right, I already spoke about our decentralized identity and trust. So here we have two extremes. Right, you can either use a fully system identity per agent, or you can just propagate the user's context through every agent. Both of them have their own flaws, and the guide acts as a way to educate and allow you to make informed decisions on which is the best approach. Ideally, it's somewhere in between the two extremes, but something to think about. And then outside that, we have P2P communication. How do you handle encryption? How do you handle like storage? How do you handle like all of the standard things that come across with standard network peer-to-peer communication? And then finally, during the build time, agent discovery mechanism might be challenging. You might have to register trust registries. How do you ensure that your Slack agent doesn't find a malicious WhatsApp agent rather than the official one? We've seen typo squatting or tool squatting happen recently, and it's or even back in the early internet days, Google with the wrong O or like using different characters can lead you to another website that looks like Google, and the same issues trickle down to agents as well. And then finally, you have runtime issues to think about, like how do you screen agent cards? It's possible you might prompt inject the underlying agent via the agent card of another agent if those guardrails are not present. So it's really important to think about all of the threats as demonstrated in the threats and mitigations guide, and use the securing agentic application guide to make informed decisions. And because we don't want to be prescriptive on saying, hey, this is the only way to do it. There's going to be various use cases and different ways to do it. And so having all possible options, threats associated with each of them, and the mitigations broken down into various phases, as Idan brought up, is really important for developers to understand. Next slide. Perfect. I'll hand it off to Idan for our surprise at the end of our presentation.
Okay, thank you, Vinith. Let me open the website. Okay, so here you go. This is the Agentic Security Hub, which is basically a website that allows you to consume the content of the document in a more interactive way. This is on your behalf, but in our side, it also allows us to update the content in a more frequent time and make sure that it stays up to date. So let's dive into the threats. As you can see over here, we have a deep dive into components, architecture, and threats. So I'm going to start with threats. And over here, as you can see, we have the entire threat landscape as described in Threat and Mitigation Guide. And if we select, for example, T1, which is the memory poisoning threat, we are breaking down the entire threat and expanding everything we can on the threat, including the affected component. As you recall, we just explained what are the key components. And memory poisoning is tied up into KC4, which are the memory modules. So all the memory module sub-modules are explained over here. And when we are going back to the threats, the memory poisoning, a threat can be executed via different attack vectors, such as data injection and context manipulation. All is explained over here. But the most important thing is actually down here, the mitigations. For each threat, we mapped several mitigations, as Vinith just described. There are various mitigations and many ways to implement each of them. For example, when we are clicking on memory validation and sanitization, we can see a deep dive into many ways to implement such a countermeasure, starting at the design phase up to the build phase, operation phase, and obviously we are providing list of tools and frameworks that can be applied to mitigate the threats. Starting with open source, moving to commercial source, everything is in the guide. So let's pivot right now to the architectures. So over here, we have all the architectures that the guide is currently focused on. Obviously, if there will be more common architectures, we will add them over here and at new versions of the guide, the Securing Agentic Application Guide. There's a breakdown of each of the architectures. Let's take a look, for example, at the reactive agent architecture. Every architecture is followed by a visual diagram that represents how this architecture should look like at the end of the day, and is backed up by real world examples. But once again, the most important things are the associated threat. Each architecture intensify different types of threats. Let's think about single agent versus multi-agent with an orchestrator. Obviously, when speaking about multi-agent with orchestrator, we have intensified the threat of memory poisoning, of communication issues between the agents. So each of these threats that intensify on the specific architecture is explained over here. And obviously the mapped into list of mitigations that can be applied and should be taken into your mind when you're choosing to implement this type of architectures. And the guide is not limited, the website is not limited to the guide only. We also extended the guide with another taxonomies, and Vinith will now explain a bit about AI SVS and NIST mappings.
Yeah, perfect. Thank you, Dan. I'm going to share my screen if you don't mind. So if you can.
Sure.
Perfect. Cool. So thank you, Dan. So let's move to the NIST mapping first initially, and then I'll show you. So NIST has a framework called the AI RMF, which is the risk management framework. Um, we've spoken to many members of the of NIST and who like developed this guide, and we realized like, hey, like a lot of we realized a lot of enterprises want to map their controls to NIST RMF to help them guide through the compliance and regulatory world. So here, what we did is we took the NIST AI RMF mapping, we mapped them to various threats and mitigations that we have. We have a detailed mapping from the NIST RMF framework to the threats and mitigations, which are also built on AI SVS. AI SVS is another open source project within OWASP, which is like the ASVS, but it's the AI security verification standard. There's around 500 plus requirements that people can follow. So let's say you're looking at user input validation for AI specifically. It's broken down into prompt injection difference, adversarial example resistance, schema type length validation, and for each of them you have actionable things you could do, like enforce instruction hierarchy or run adversarial evaluation tests, sanitize third party content. And each of them are broken down to levels similar to how it's done for the ASVS currently for our application security. And so all of these are then mapped to the NIST framework. Here we have a pretty graph. Let me move to a white background so it's easy for you guys to see. So let's say you take let's say you look at the NIST measure or NIST govern or manage part of the framework. Here you can click on any of the five subcomponents. Oops, sorry about that. And then here you should be able to click on any of the actual like RMF requirements, and you can see how they map to the AI SVS. And there's also like strong details down here. If you're more of a visual learner, mapping your NIST to various AI SVS controls, as well as the threats and mitigations and so on. And finally, we in the at the high level, we've also created like an architecture like visualization that allows you to look at. Let's say you just want to look at the various architectures and components. You can see how each like one component how is shared amongst different architectures. If you want to see how threads are mapped to components, you can see like, let's say this thread which is intent breaking is mapped to which components and so on. Or you can also map threats to mitigations like we've spoken about. So this makes it a really visual, easy to understand, easily digestible, and quickly updatable format. There's the same guide that we have that we can keep updating as we go on. Another thing Idan and I would like to point out is this is a fully open source project. You can just go all the way to the bottom to the GitHub. You will be able to contribute directly to it. We also have references and links to a lot of like guides that we've compiled that we've used to build this. And I would like to thank everyone in the open source community who have helped us. Tomer, Emil, John, Ron, everyone from the OWASP, ASI, Rob, Idan, and everyone else who helped build this as well. Perfect, Idan. Any final thoughts before we say goodbye?
Um, I think that like final message is that we truly hope that this guide will be useful for everyone in the community. We put great effort in compiling it, and every time there's a new framework out there, new mitigation techniques that you guys found useful, please feel free to contact with us so we will extend the guide, extend the website, and we'll release new version of the document. Feel free to contact with either of us. And I think that's it. Thank you very much.
Yep. Thank you so much. And I would also like to thank the OWASP. Rob, who's unable to make it here, was also a co-lead on this project, as well as John and Ron, and the rest of the OWASP GenAI project board for enabling us and uh, helping us, bring out these useful materials to all of the developers. Thank you.